नमस्कार, सादर स्वागतम, अभिनंदन, केम छो, जय श्री कृष्णा, वणकम, आदाबर, सत श्री अकाल, खंबागानी, राम राम एंड वेरी गुड आफ्टरनून। मैं अनिल भारद्वाज आप सभी का पीआरएल के 119वें अध्याय में स्वागत करता हूं, अभिनंदन करता हूं। आई अनिल भारद्वाज very warmly welcome you all to the 119th PRL Kamrit Vyakhyaan. As you all know, we started the PRL Kamrit Vyakhyaan as a part of celebration of PRL's 75 years of establishment, which coincided with the Azadi Kamrit Mahotsav. And it was meant to celebrate the 75 years of legacy of PRL in the area of space sciences and physics. PRL, as you all know, was established by Dr. Vikram Sarabhai in the year 1947. And we wanted to celebrate this in the period when it was COVID, so we started it online. And that also helped us that we were able to do every Wednesday, 4 p.m. every week, continuously for 75 episodes. After completing that milestone, we took another sankalp that we should have a PRL Kamrit Vyakhyaan 2.0, which should be every month, one Vyakhyaan, and that should continue till PRL completes its century of 100 years of establishment. So with this brief background in terms of what PRL Vyakhyaan is all about, today, that is 27th of August, 2026, 4 p.m. Thursday, we have yet another very distinguished Vyakhyaan Karta with us today, Professor G.C. Anupama, who is currently INSA senior scientist, but she has many portfolios in the past, and we will hear the details about that from our colleague. She is going to give her Vyakhyaan on time domain astronomy, a peek into restless universe. So we all are restless, but universe is also restless, and that is what we are going to learn from the Vyakhyaan of Professor Anupama. We really like to thank Professor Anupama for agreeing to our invitation and to be with us today at this Vyakhyaan. And we would now request Professor Nandita Srivastava to kindly introduce our Vyakhyaan Karta to the colleagues who have joined us live on the PRL's WebEx, as well as those who have joined live on the PRL's YouTube channel. So over to Professor Nandita for introducing today's Vyakhyaan.
Thank you, Professor Bharadwaj, and good afternoon, everyone. It is my honor and pleasure to introduce today's speaker, Professor G.C. Anupama, who is one of India's leading observational astronomers. She is also the former Dean and Senior Professor at the Indian Institute of Astrophysics, Bangalore. As most of us know, she did her PhD from Indian Institute of Astrophysics, and then she moved on to IUCA as a postdoctoral fellow, and before returning to IIA as a faculty member. Her research interests focus on transient phenomena in the universe, especially those related to the final stages of stars. She has also contributed very significantly to the development of astronomical facilities in India. She led the commissioning and science verification team for the 2-meter Himalayan Chandra telescope at the Indian Astronomical Observatory in Handley, Ladakh, and served as the professor in charge of the observatory during 2014 to 2021. Uh, as the Indian PI of the International Growth Project, about which I believe she is going to talk today, she worked as the PI and of the Global Network of Telescope for the Study of Transients. She has led this successful installation of a 0.7-meter wide field robotic telescope at IAO, the Growth India Telescope GIT. She was also a key member of the Indian core team engaged in the international project to establish the 30-meter telescope TMT in Hawaii, US. As the lead of the India TMT optics group, she played a significant role in establishing a one of its kind world class facility for polishing large optics at the Crest campus of IIA. Professor Anupama has led the initial work towards site characterization and development of a detailed project report for the National Large Optical Infrared Telescope (NLOT). She is also a fellow of all the three Academy of India, Science Academies of India, that is National Academy of Sciences, Indian Academy of Sciences, and Indian National Science Academy. She's a recipient of the Government of Karnataka's Sir C.V. Raman Young Scientist Award in the year 2001 and the ASI Zubin Kimbhavi Award for observational and instrumentation work in astronomy and allied fields for the year 2025. Professor Anupama has served as the president of the Astronomical Society of India (ASI) from 2019 to 2022 and holds the distinction of being the first female president of ASI. I recall that I worked when she was the president of ASI. I was given the charge of co-chair of the Astronomical Society of India meeting, and it was a privilege to work with her, especially when that year was a COVID year, and we managed to sail through. We managed a large number of people to connect. I think there were more than 600 people online. So thanks to her leadership in all the fields that she has put her hands on. She is currently the editor in chief of the Journal of Astrophysics and Astronomy, published by Indian Academy of Sciences. I have the honor and privilege to work with her as the editorial board member and have had very fruitful interactions and learned a lot from her. So, with these words, I invite her to give today's lecture on time domain astronomy. We are all looking forward to your lecture, Professor Anupama. Thank you.
Thank you, Nandita, and thanks to Professor Bharadwaj. I would like to thank you for inviting me to give this talk today. And I hope I can convey some of the excitement that I feel in this subject. So without much ado, let me share my presentation. Sorry. Are you seeing my presentation?
Not yet. We see the full screen.
Okay, just a second. Let me stop sharing and then. And we did try it out, but now it's not. Okay, do you see it now?
Yes, we can see.
Okay, yeah, okay. So, as I titled it, I mean, the time domain astronomy is essentially a peek into the universe, which is restless, quite unlike what we believe or think that it could be, like a steady state, but it is not really that. So, what do I mean by the universe being restless? There are a lot of variable objects in the sky, and so the universe is filled with short lived dynamic events which change in brightness or their behavior over relatively short periods of time. And what is time domain astronomy? Time domain astronomy is basically the study of these variations, and it is a study of the lifetime evolution and changes of a wide variety of cosmic objects, particularly when these changes happen over a short cosmic time scales of the order of hours to a day, to days, or a year. And such rapidly varying objects are termed as transients. So today's talk will be all about transients, the different kinds of transients that we know as of today. Okay. So what are these objects? Now, transients are basically the result of some kind of explosion or collision that leads to a change in the physical character of the source. Okay? And some examples of this are supernovae, gamma ray bursts, or compact object mergers. Transients can also result as a result, can also occur as a result of accretion of matter, leading to phenomena like the nova outbursts or the tidal disruption events or flares in active galactic nuclei. Now, these events are highly unpredictable and they show a temporal evolution of the physical conditions. And once they brighten up and they fade, they often fall below the detection threshold when they're faint. So it's like when these phenomena occur, you see a sudden brightening and it seems like there is a new object in the sky. Okay, and then it fades out very fast, and hence they are known as the transients. So why are they interesting? Okay, they're interesting primarily for the main reasons being that they occur over all distances, and hence they serve as excellent cosmological probes. You have transients in the nearby universe as well as in the most distant universe. Okay. Now we know that the standard cosmological probes or the distance, primary distance indicators are the Cepheids or the RLI stars. But transients such as supernovae, particularly of the thermonuclear kind supernovae, can also serve as excellent cosmological probes. Okay? And indeed, it is these type of supernovae which led to the discovery of dark energy. Also, exploding stars produce produce extreme physical systems. They lead to formation of neutron stars and black holes. And when neutron stars and black holes merge, they give rise to gamma ray burst events and gravitational waves. So you can understand the extreme physics through the study of these objects. They also lead to the chemical enrichment of the galaxy. For example, novae are a good source of lithium. Supernovae are the source of almost all elements in the universe except hydrogen, helium, and lithium, and hence they are excellent laboratories to study nucleosynthesis, particularly the formation of our process elements. And when neutron stars merge, they produce some of the heaviest elements and very interesting elements like gold, platinum, etc. So that's why transients are interesting. On the right, you can see a cartoon which I have adapted from the ASI vision document, which shows the synergy of the study of transients with various other fields in astrophysics like cosmology, gravity, AGN, and even with respect to stellar populations, magnetic fields, and radiative processes, almost everything, including observing facilities, computation, and data science. So the study of transients encompasses practically everything in astronomy and astrophysics. So how do we observe these objects? I said that these are, they just kind of, they're unpredictable. So you don't know where they're going to occur. So how do we observe them actually? This is done through optical surveys, which is generally done with small telescopes, small wide field telescopes that are scanning the sky every night. Different parts of the sky are scanned every night, and I've given here some examples of these surveys. The pan stars, it consists of two telescopes. These are all in the optical, and they have a cadence of a monthly cadence. So what this means is that once in a month, it goes back and observes the same region of the sky. And the main purpose for which this survey was set up was to discover supernovae and also observe near Earth objects. This survey has been active since 2010 and has discovered a lot of transients. Another highly productive survey is the one conducted by the Zwicky Transient Facility, or the ZTF. This is a 48-inch Schmidt telescope, which has a cadence of 2 days. And it is the purpose was obviously to detect and follow up transients and near Earth objects, asteroids. It's been active since 2017. The other two important surveys are the Atlas survey, which is a global network. There are several telescopes located at different parts in the world, and they have a nightly cadence, and they detect asteroids and transients, and it has been active since 2015. The other one is the All Sky Automated Survey for Supernovae, also abbreviated as ASSASSIN. And this is also a global network. It has telescopes located in the northern and in the southern hemisphere with a nightly cadence. And primarily, it was set up for observations of supernovae, but ASSASSIN has also been detecting other transients. This has also been active since 2015. Now, these are all small telescopes. Very recently, the Vera Rubin Observatory telescope, the 8.2 meter wide field telescope, has come online. This will be conducting a 10-year survey of the sky. And with this, we can expect thousands of new transients. Practically per night, you'll be expecting a whole lot of transients at very faint levels to the level of 25th magnitude. It is expected to produce about 20 terabytes per night or 15 petabytes per year. So this is going to be huge, and it is going to change the scene of transient astronomy. So having said that, I mean, how actually are we going to detect this variable source? This is done by a method called image subtraction method, which was first utilized by Leavitt in 1908. For using this method, she actually detected Cepheids in the Magellanic Clouds. Okay. So what she did was, like, she used photographic plates. Those days, photographic plates were the detectors. And she made a single positive plate from one of the many glass negatives and used that against the gray background of the plates that were used for observations, which are in the negative form. Okay, so using this, one could neutralize the unchanging stars, and the stars popped up from the negative. Okay, so this was a physical subtraction method, but today with the digital data, we can get a reference image and subtract it out from the object frames, from the new observations, and we are left behind with new sources which are not there in the reference frame. So this is how you detect the variable sources. But mere detection is of limited value. So basically, we have to also follow up. Classification of these sources and follow up are the key here. Okay. So as I said earlier, for example, with the LSST, you're going to have petabytes of data. We are already having terabytes of data available. And what is extremely important and what has turned out in the recent years is that you need a rapid follow-up, which basically means that you need real-time transient detections. And not just detection, you need to communicate rapidly about the detection of these transients to the community so that there can be rapid follow-ups with multi-wavelength facilities. And this is best done through international collaborations. So there are several algorithms which are used today for the difference imaging. And as in every field, the use of AI and machine learning have become essential in handling these massive volumes of data. Now, having detected this, one needs to find the outliers and reduce the contamination, take care of the noise and spurious sources. So all this can be done through the machine learning, and classifications are also being done through machine learning. And then you cross match with the various catalogs to make sure that the object that you have detected is new and it is not an already known source. Okay. Now, having done that, there has to be a rapid and efficient dissemination of these discoveries. So, how is this done? This is done by real time alerts, which are automated and standardized. And this is through the alert brokers. So, what are these alert brokers? These are basically software systems that ingest, process, and distribute the alerts from the surveys to the scientific community, thus facilitating real time analysis and follow up the transient events. There are several alert brokers available today and communicating. And after having alerted, there is a rapid reporting through astronomers' telegrams or the General Coordinates Network, the GCN, which is basically NASA's time domain and multi messenger alert system. So, for example, when there's a GW event detected, there is a GCN alert sent out within about 30 seconds. And if you take any of these survey, for example, the ZTF is tuned to immediately follow up and monitor using other facilities. And also there are centralized databases and repositories for transients, like the transient name server, which puts out and sends out these alerts on the discovery of these transients. And through the international collaborations that have been established, one can have an immediate follow up. Sorry, did something happen here? Yeah, okay. Are you seeing the slide?
Yes, yes, we are seeing it.
Okay, thank you. So one such international collaboration is the growth project that Nandita mentioned. This is basically a collaboration of astronomers across the globe who have access to various observing facilities across the globe. So the growth is a short form for Global Relay of Observatories Watching Transients Happen, which essentially means that through this international collaboration, a transient can be followed up for almost 24 hours. Okay. There are three facilities in India: the Himalayan Chandra Telescope, the GMRT, and the Growth India Telescope, which are part of this international network. And the growth collaboration within India is led by IIA and IIT Bombay. So, having given this introduction to how transients are detected and what are the transients, let us go on to some examples of transients, particularly the ones that I have been interested in. The first of these are the NOVA systems. Now, what are novae? These are basically interacting binary stars where you have a white dwarf primary and a main sequence M star secondary. The white dwarf is accreting matter from the secondary, and at the boundary of the accretion disk, when it builds up to a critical temperature and pressure, hydrogen burning sets in, and this soon builds into a thermonuclear runaway reaction. So when this runaway reaction happens, it releases a lot of huge amount of energy to the accretion disk, causing the disk to expand and be ejected from the system. When this matter ejection happens, the nova explosion occurs. And this explosion is accompanied by the release of energy in the range of 10 to the 38 to 10 to the 40 hertz, and with ejection of matter with velocities higher than 500 kilometers per second. There are some objects which show multiple nova eruptions with a recurrence rate of a few years to several decades, and these are termed as recurrent novae. So, the study of these systems is confined to the study of the physical conditions in the ejected material, understanding the geometry, temperature, density, abundance, interaction with the surrounding medium, and also understanding the property of the binary components, including the accretion phenomena. So, some examples of the kind of results that we can get through multi-wavelength observations of novae. Here is an example of the recurrent nova 3890 Sagittarius. During this 2019 outburst, we observed this object with the astrosat in the soft X-rays, in the optical with the HCT, and in the radio with the GMRT. This nova showed very clear signatures of a shock interaction. In the optical, it showed a decrease in the velocity through the narrowing of the emission lines and through the emergence of the coronal lines during the early decline phase. And in the radio, the detection of the low frequency radio emission, which was very well modeled by non-thermal emission, all this was signature of the shock interaction. The super soft X-ray observations, which basically come from the remnant nuclear burning on the surface of the white dwarf, that is in the remnant accretion material that is left behind. We found the super soft source to be highly variable over time scales of hours during the emergence of the super soft phase. And we found that we could fit the supersoft emission very well by a non-local thermal equilibrium model, which is used for white dwarfs, confirming that the emission is coming from the surface of the white dwarf. So together, the optical, X-ray, and radio data all indicated the presence of a clumpy material in the environment. And the mass which was ejected was found to be 2 into 10 to the minus 6 solar masses. And with an estimate of an accretion rate of 2 to the 10 to the minus 7 solar masses per year, and looking at the recurrence rate, we find that not all the mass that is accreted onto the white dwarf is ejected during the outburst. Now, this is an important result because this indicates that the white dwarf in this system has the potential to increase its mass, and eventually it could become a supernova of type 1a. Another interesting object is the recurrent nova RSO-Vyakhyaan. I give here the example of its outburst in 2021, which again had multi-wavelength observations with the optical from HCT, astrosat observations of the super soft X-ray source, and the radio observations using the GMRT. Even in this system, we had strong indications of a shock interaction. Now, this outburst had been studied during its 2006 outburst in the radio, which was the first, when for the first time we had detected low frequency radio emission. Comparing the 2021 outburst with the 2006 outburst, we found that the CSM density, that is the material, the circumbinary material around the system, has a variable density, and it is not a uniform material around the system, with giving rise to differences in the radio emission that we find in the two outbursts. Another nova which also had multivalent observations, for which we had the FUV spectra again from Astrosat, is a classical nova. And this particular nova showed modulations in the X-ray flux during its super soft phase. While in the X-ray we found modulation, there were no such modulations seen in the FUV data or in the optical data. So based on all the data, we conclude that this nova is it's a neon nova, which means that the white dwarf is an oxygen neon magnesium white dwarf, and and this is also corroborated by the emission lines that we see in both the optical and in the ultraviolet. Another recurrent nova which was observed is the recurrent nova T Pixidus. We observed the 2011 outburst. For this nova, what we found is that the Nova changes its spectral type from helium nitrogen dominated spectrum to iron dominated spectrum around the maximum, and then again it goes back to the helium nitrogen dominated type of spectrum, indicating that we are seeing emission from different regions at different times. So we modeled the ejector using the line profiles and find a bipolar conical morphology with equatorial rings at an inclination of 15 degrees. And interestingly, we also find that there is a difference in the elemental distribution, with the oxygen and the nitrogen lines coming mainly from the outer regions, while the hydrogen lines come predominantly from the inner regions. So, this is a clear indication of stratified distribution of the elements in a nova ejector. Moving on to the next kind of transients, the supernovae, which we have been observing very extensively from IAO. So supernovae are classified based on the early spectral properties, and I don't have to tell what a supernova is. It is basically the end stage of a star, signifying the death of a star. Okay. So based on the spectral properties, it is classified into different types. The hydrogen-rich types are called the type 2s, and the hydrogen depreciant types are called the type 1A, ones, of which the type 1A is coming from a white dwarf explosion, whereas the type 1B and 1C are coming from massive stars. Type 1A is the thermonuclear type supernova, whereas all the others, which come from massive stars, are known as the core collapse supernovae. So type 1A, as I said, it is coming from the explosion of a white dwarf. Now, how does this happen? We know that when the white dwarf crosses the Chandrasekhar limit, its mass crosses the Chandrasekhar limit, it becomes unstable. So these supernovae are the result of explosions of carbon-oxygen white dwarf. Now, how can the white dwarf increase its mass? It can do so by accretion of material from a companion in a binary system. And this companion can be a normal star, or it can be another white dwarf. Now, if it is in a system with a normal star and a white dwarf, it is known as a single degenerate system. And in a system where you have two white dwarfs, it's known as a double degenerate system. In the double degenerate system, it is believed that the white dwarf merge together, giving rise to a supernova explosion. Now, what is the mechanism of the supernova explosion or type 1A supernova explosion? It can be either a pure detonation, where you have the burning front propagating at supersonic velocity. And in this case, the explosion converts the entire mass of the white dwarf into 56 nickel. But theoretical models were not very efficient in producing the intermediate mass elements that are actually seen in observations. So it is not a favored model. The other model is the slow burning or the deflagration model, where the burning propagates at subsonic velocity, and it has unburned material, but this can create IMEs. Okay, but this also does not reproduce all that is observed. The third model that has been proposed is the deflagration to detonation transition, or the DDT model, or the delayed detonation model, where you have the explosion beginning with a subsonic deflagration wave that reaches supersonic speeds and leads to the detonation of the white dwarf. Now, this model has found to be the most successful model for the normal type 1A supernovae. Now, core collapse supernovae arise out of massive stars. We know that the stars synthesize elements, and in the case of massive stars, they can synthesize all the way to iron in the core. Okay? So, when such a thing happens, you have iron in the core with layers of the other elements in the outer shells, as shown in the cartoon on the right. Okay? Now, there can be no further fusion beyond iron, but then there is still continued making of iron. When this happens, the core keeps gaining mass. It comes to a stage where it can no longer withstand its own weight and it implodes. So, this implosion or the gravitational collapse rebounds off the degenerate core, leading to a shock wave, which moves forward into the surrounding material and transfers the energy to the outer regions, giving rise to the supernova explosion. So, when the supernova explodes, there is a sudden brightening followed by fading, and this temporal variation of the luminosity is what we term as the light curve. Now, as we can see in this plot in the right, the top right, there is a variety of light curves that are seen in the case of supernovae, with all of them showing a rapid rise but differences during the decline. Many of them have a linear decline of the luminosity, but there are some which show a plateau for a fairly long time of the order of a few hundred, of the order of 100 days. Okay, and these are called as a type 2p supernovae, which is the hydrogen-rich supernovae, and the plateau is primarily due to the recombination of hydrogen. What are the primary sources of energy here? The shock breakout, the shock cooling and the ejecta recombination, and the radioactive decay from 56 nickel to 56 cobalt and eventually to 56 iron. The cobalt to iron decay is the towards the late phases is what you see there. While these are the primary sources of energy, there are secondary sources of energy like the interaction of the supernova material with the circumstellar material can also give some amount of energy, which is reflected in the light curve. The neutron star, which is formed, you can actually have a magnetar forming, and the rotational energy of this magnetar can also power the light curve. In some cases, you can have a fallback of the outer regions onto the degenerate core, creating a fallback accretion, and this can also power the light curve to some extent. The spectroscopy of the supernova, any supernova for instance, provides you a scan of the entire stellar explosion. So with time, we begin to see as we probe, deeper into the supernova ejecta and go closer to the core, we begin to see the different elements, which are a reflection of the nucleosynthesis um, that the supernova has undergone, not just during its stellar evolution, but also during the explosion itself, when it forms the R post process elements, that is, the heavy elements are formed. So, modeling the light curves and the spectra can provide you information about the explosion energy, the velocity you have, the amount of mass that is ejected, the kinetic energy in the explosion, and it can also provide you information about the progenitor mass. So basically, how are we doing the supernova observations? I mean, we use the 1 to 4 meter class telescopes that are available in the country. We do a detailed long-term monitoring of the evolution of the light curve and the spectrum and studies temporal evolution. And with the modeling, we estimate the explosion parameters and the nature of the progenitor. Also, radio observations will provide us information about the progenitor as well as the environment. So a few examples here. I mean, we have been studying low redshift supernovae of type 1a. This is particularly important because if we want to use the supernovae type 1a at the higher redshifts as cosmological probes, we need to really understand these systems. The observations of supernovae of type 1a, initially these objects were thought to be highly homogeneous, but with the number of such objects being observed, being discovered and observed in detail, it is found that there is a certain amount of diversity in these objects. So it is extremely important to understand the causes of the diversities. And for this, the best way to do this is to study them at the lower redshifts. So we have been observing several supernovae of type 1a in the optical and supplementing the data with UV and NIR. And as I said earlier, we also do some amount of analytical modeling to understand the system better. So what is the kind of diversity that you see and what is it due to? One is primarily because of the nature of the progenitor. I told you earlier that we can either have a single degenerate or a double degenerate progenitor. So this can also give rise to some amount of diversity in the observed properties of this supernovae. Okay? So the early spectra will actually allow us to test whether the supernovae of type 1a, whether they are arising from a single degenerate or a double degenerate, or in some cases you can also have what are called as the subchandra scenarios, where you can have a white dwarf explosion with the mass of the white dwarf being lower than the Chandrasekhar mass. Or you also have cases where you have a high luminosity type 1a supernova, which is probably coming from a white dwarf with the mass much higher than 1.4 solar mass. So it's important to understand this and also to understand the physics behind these various types of progenitors. And the diversity can also be due to the explosion mechanism itself, whether it is deflagration, whether it is detonation, whether it has happened in a spherical manner or is it an aspherical explosion that gives rise to asymmetry in the ejecta. This can also produce diversity. And it is seen that the host galaxy properties also, like whether it is occurred in a spiral galaxy, in the spiral, whether it is in the spiral arms or in the bulge of the galaxy, or it has occurred in an elliptical galaxy, also has an effect on the observed property, particularly in the luminosity that is seen. So what is seen is that 64% of the type 1a supernovae are what we term as the normal type 1a, which essentially means that these are well explained with the variation of the luminosity with the time it takes to decline. And these are termed as the normal supernovae. There are 20% which are overluminous and about 16% which are subluminous. The figure on the right shows what is called as a period luminosity relationship for type 1a supernovae, popularly known as the Phillips relation, because it was Phillips who first gave this relation. This Phillips relation is what leads to type 1a being used as cosmological probes. Okay? Helps in them being used as cosmological probes. So in this plot here, the line that you see, that corresponds to the normal type 1a supernovae, and then you have the other kinds, which are the fast decliners, which are the high luminosity superchandra ones, and the low luminosity supernovae. Now, spectroscopically, we have seen some diversity with some of these systems, even in the normal type 1a, showing high velocity features of calcium and silicon, which are not normally seen in most 1as. And this is probably because of the presence of shells or disks or some progenitor material which is causing overdensities in the supernova spectrum. A few examples of the diversities that we have observed. A very interesting normal type 1a supernova 2011 AA. It fitted well with the period luminosity, but what we found is that it is the slowest declining type 1a detected so far. And spectroscopically, it had some peculiarities in the sense that it showed unburned carbon at a velocity lower than silicon. It means that we had unburned material inside the supernova, outer layer of the supernova ejector. So when the white dwarf exploded, there was still some unburned material, which indicates some kind of an asymmetric explosion. So fitting various models to this, we arrived at a conclusion that this particular supernova could be a result of a violent merger of white dwarf with mass greater than zero point 0.9 solar masses. And this kind of a violent merger could have caused an asymmetric explosion, leading to some amount of unburned material seen in the very early phase of the supernova. The other very interesting peculiar type of supernovae are what are called as the type 1ax, which do not follow the period luminosity relation, the Phillips relation. These are fast declining, low luminosity and low velocity supernovae. Normally, the fast declining supernovae have low luminosity, but they also have a high velocity. The slow declining, low velocity supernovae, normal type 1 is supernovae, are with high luminosity, whereas these are fast declining, low luminosity with a low velocity. So these seem to form a different subclass of type 1a supernovae, and not many are known. They form a very small fraction of the known type 1a supernovae observed so far. And it is probably that these arise out of single degenerate deflagration explosion models, which seem to be fitting most of the 1a axis. Let me quickly skip over to the core collapse type of supernovae. We have studied the standard type 2p supernovae, and another interesting class of these plateau supernovae are the ones with have a short plateau, probably because of an excess mass lost during the progenitor's evolution. And it was speculated that the mass loss is higher in these systems because the primary could be more massive. However, we have studied some of the short plateau and found them to have a lower mass. So we have short plateau type 2p supernovae arising over small, so lower mass progenitors. Okay. So we show that the progenitors of the short plateau supernovae are not necessarily the ones at the higher mass end, but these also arise from the low mass end, and probably they are in a binary system, which could have led to a higher mass loss rate. We observed this very interesting brightest supernova since 1987A, brightest in the recent years. And we observed it with AstroSat and obtained the FUV spectrum. This is the first FUV spectrum of a supernova observed till date, and particularly at a very early phase. So in this particular supernova, we found that there is a circumstellar material which probably was a result of an enhanced mass loss just about 30 to 60 years before the actual supernova explosion itself. There were strong signatures of this. We could see we could observe the initial shock breakout, the flash ionization, and the continued observations showed that this is arising from a low mass progenitor. And in addition to the CSM that we found very early on, there's also CSM material corresponding to a much earlier mass loss, which is at an extended location. Let me skip this and go to the other kind of objects, that is the gamma ray burst sources. These are short-lived bursts of gamma ray photons, which can be from a few milliseconds to several minutes, and they occur at cosmological distances. We have the long bursts, which last for minutes, and the short bursts, which are lasting for the millisecond kind of time. Both these events create a black hole and a disk of material around it. The whole disk system pumps out a jet of material very close to the speed of light. And when this jet is in our line of sight, that is when you find this intense burst of the gamma ray. And it is this jet which causes this high luminosity. It releases an enormous amount of energy of the order of 10 to the 53 ergs. Now, several gamma ray burst sources have been observed, and we observe the optical afterglows or the afterglows in multiwavelength region, not just the optical, but also radio, X-ray, and infrared, using various facilities. A couple of interesting examples is that in one of them we found a flaring detected about 7 days after the GRB event itself. And we interpret this as being most likely to the activity of the central engine. In the long gamma ray burst, people have found associated supernovae with the long gamma ray bursts, which are termed as the hypernovae because they are extremely luminous and coming out of high mass core collapses, and the mass being much higher than the ones which lead to the supernovae. The other object which is interesting is GRB 230204b, where we detected the optical afterglows just about an hour and a half after the Fermi trigger of the gamma ray burst. And in this particular gamma ray, we explained this to be arising out of a Wolf-Rayet primary progenitor that had experienced moderate mass loss. Now, very recently, as recent as in 2018, a new class of transients were detected. These are the luminous fast blue optical transients, the progenitors of which are not yet known. There could be multiple progenitors for this. It could either be the stellar collapse, or they could be tidal disruption events. There could be merger of white dwarfs. It's open. It's not known. There could be different progenitors, different central engines. Are they this transients that we already know of but being viewed differently, or are these a new class of transients? Is still not known. Like, for example, the first of this, which was detected, the 2018 COW. In this case, it was the progenitor type is not very clear what it could be, but what is known is that there was a dense CSM very close to the progenitor, so it could have been massive star progenitor. However, other objects of this kind, the AT2020 XND, is found to be clearly consistent with an accretion-powered jet following a direct collapse to a black hole, which means a collapse of a massive star, most likely. And on the other hand, another FBOT was found to be more of a tidal disruption event, a jetted tidal disruption event. In fact, it is the first of its kind known. So this indicates that there are very interesting transients that we are seeing, and with LSST, there could be a lot more new transients that we begin to see. Okay? The last of the transients, and something which is very interesting of late, is the detection of the gravitational waves and particularly the electromagnetic counterparts. Now, gravitational wave, the astrophysical sources which could give rise to the gravitational waves could be the inspiral and merging of compact binaries, the stellar core collapse, or rapidly rotating asymmetric neutron stars, a black hole ring down, or from the early universe phase transitions. Okay? What do the electromagnetic observations tell us? They will give an indication of the nature of the source itself. It can actually help in pinning down the position of the sources because the GW detectors, that is the LIGO, Virgo, Kagra, have a very large localization. So the detection of an EM counterpart will pin down the actual position of the source. It can help us identify the host galaxy and the environment. The first binary neutron star merger that was observed, that is GW 170817, which all of you are aware of, luckily for us had an electromagnetic transient detected, which was very well studied. And subsequently, unfortunately, we have not had any EM detected. But very recently, there was a very interesting source where the LIGO, Virgo, Kagra detected or reported gravitational waves from a subthreshold binary neutron star merger. Now, if this source is astrophysical, then at least one neutron star was below a solar mass. So, quite interestingly, we found an object within this localization area which was varying and which showed initial properties which were reminiscent of the kilonova detected with GW 170817. But subsequently, it showed properties very similar to young stripped envelope type 2 supernovae. So while most people believe this to be a type 2 supernovae, we propose that what could have happened is that there could have been fragmentations which led to subsolar neutron star forming, which merged with the core which was left behind in the formation of this supernova, giving rise to what we term as a superkilonova. Okay, if you had a supernova explosion, the ejecta fragmented, there were fragments in the ejecta which gave rise to a subsolar neutron star which merged with the central neutron star, the neutron star which is formed in the supernova explosion, and this gave rise to these gravitational waves. So very quickly, as I said earlier, we have 1 to 4 meter class optical telescope to study these objects. And we have in the other wavelengths, we have GMRT, AstroSat, and MACE. But none of these are dedicated for studies of transients. There's only one facility, that I'm aware of, if I'm not wrong, that is dedicated for the study of transients, and that's the Growth India telescope, which was funded as a part of the growth project under the International PIRE program. by DST SERB and administered by IUSSTF. It is a 0.7 meter wide field telescope. The primary camera is Android 4K by 4K system, and we have two other smaller cameras which we can use. So this telescope is it operates in a fully autonomous mode. While we generally observe in a targeted mode, we can also do a tiled mode of observations, which is particularly useful for transient search. And we can also do the non-sidereal mode of observations for fast-moving targets such as comets, asteroids, near-Earth objects. So these observations are monitored by Slack bots automatically, and we also get alerts through these Slack bots. There's a dedicated data pipeline analysis which helps in the registering and the differencing to detect new transients and also do photometry. Coming to the performance, initially we were operating it in the manual mode when we had just about 30% on-sky efficiency. And once we went into the automated mode of observations, on an average, we have 85 to 90% efficiency. It's a highly efficient telescope, can go fairly deep. In 10 minutes, we have been able to reach 21.5 mag in the STSS R band. And with this, we have been, trying to follow up the detection for electromagnetic counterparts of gravitational wave sources during the O3 run as well as the O4 run of LVK. Over 250 GRBs have been followed up, and the magnitudes reported. Several supernovae are being monitored, some of them with very detailed monitoring of the light curve. And we are also doing a survey of the M31 for detection of novae in M31. And we have detected about 75 novae which were reported since 2022, since we started the survey. And also we discovered one nova for which we did follow-up observations using the HCT, Keck, and the Palomar 5-meter telescope and did a detailed analysis. So in the future, as all of you know, in the recent budget, there were two optical facilities that have been announced. One is the upgraded HCT, which is going to be a 3.7 meter wide field rapid response segmented mirror telescope, which will be a pathfinder to the National Large Optical Telescope, which is going to be a 13.7 meter segmented mirror telescope. But what would be nice to have is a network of 1 to 2 meter class wide field telescopes across the country dedicated for the study of transients with multiband photometry and spectroscopic capability. And this has actually been recommended in the ASI vision document. Now, of course, I mean, we are going to have LIGO India, which will help in the multi-messenger astronomy by improving the localizations and hence, help in rapid detection and follow up with other messengers like the EM or the neutrino detectors. And we will have, with respect to the international facilities, we'll have access to the square kilometer array observatory in the radio and with the 30-meter telescope in the optical and infrared. So moving forward, continuous observations of the transient phenomena is crucial for answering fundamental questions. As we develop better instruments, harness artificial intelligence, and engage in international collaborations, time domain astronomy will continue to play an increasingly central role in exploring the dynamic and energetic universe around us. And ultimately, this field will shape our understanding of both the grand scale structure of the cosmos and the most intimate details of high energy astrophysical events. And as you can see in these two plots that I've shown here, in 2007, there was a large gap in this phase space plot, which was practically with no known objects. But as of today, we find that is already filled in, and it keeps getting filled in more. So with this, I'll stop. Thank you.
Thank you, Professor Anupama, for giving a very insightful talk on time-domain astronomy and emphasizing on the need for multi-messenger observations. So now I think we have some time for question answers. So those who want to ask questions, please raise your hand.
Can I stop sharing?
Yes.
Because that will help me see the. Okay.
So let me begin. I mean, because I do not see any hands raised right now. So I'll have a couple of questions. So my first question is related to this Vera-Rubin Observatory large area survey. So that is likely to discover large number of transients, and one of the challenges would be classifying them. And you mentioned about the automated classification. So what strategy would likely to be opted? I mean, is it like that you would have a template of light curves or spectra, and then one would match and see that what kind of class, what class of the source is?
Yeah. Actually, that is what is being looked at. So what is being done is that you have these templates of light curves for different, transients, right? And LSST, for example, it will observe in the various bands. So the color information is going to be crucial in classifying various types of transients. And that you, with the known transients from the nearby universe, you have, as the transients vary, how the color information, how the color varies also, you have that information. So that also needs to be put in. I mean, of course, the caveat here is that we're assuming that the way these transients behave in the nearby universe is the way it's going to behave in the distant universe. I mean, LSST would be probing up to much larger distances than what we can today, right? So that caveat is there, but nonetheless, you take care of that. I mean, you have, of course, the color will also have to be corrected for the redshift and everything, but then the color information is going to be crucial.
Okay, thank you. Other question is related to, you mentioned about the type 1A supernovae, and you said that there is a diversity, and then there is a 60% are normal, and then 20% are overluminous, and then 16% are underluminous. So is it possible that some of these overluminous or underluminous sources could be a normal, but they are being observed at a different phase of evolution? Is it possible?
That possibility could be there. Okay, I mean, they are probably normal in the sense of the explosion mechanism is similar. Okay, they are arising out of white dwarfs explosion mechanism is similar. Okay, in that sense they could be normal, but the overall, the underluminosity could be if there is an asymmetry in the explosion, for instance, right? And then, depending on how you're looking at it. Okay, so this can cause some differences. So what is termed as normal is primarily those objects which follow the luminosity width relation, the Phillips relation.
Okay.
And these are the ones which are the best candidates for the distance ladder, because they can be well calibrated.
Yes, there is a question by Professor Navindra Singh. So you may ask.
Yes, Navinder, you can unmute yourself and ask question if possible.
Yeah, thank you, Risha. Thank you, Manish. Yeah, so Anupama, thank you for the colloquium. Wonderful discussion. My question is related to, you mentioned somewhere that there are super Chandrasekhar limit cases, white dwarfs. So how they survive? Because the electron degeneracy pressure will not be able to sort of stabilize such systems, and then is it some rotation, very high angular momentum, or magnetic fields play the role, or what is this thing?
Yeah, that's what the theoretical models, they say that it could be with high rotation, they could have a magnetic field which allows them to survive. Okay. Or the other way of having these high mass super Chandrasekhar white dwarfs could be that when you merge them. So when you have a double degenerate white dwarf system, and these two white dwarfs merge together, okay, they could merge in such a way that they form a single white dwarf which is exceeding the Chandrasekhar mass.
So, but how then the electron degeneracy, how it sports the mass greater than 1.4 actually?
Sorry,
I mean,
how?
what is the, so how the stability, what is, how does the star become stable? I mean, like,
No, it
I mean,
doesn't become
the
stable.
electron
It explodes.
degeneracy,
This is during the merge. It merges and then during the explosion. Okay.
I see it's a temporary situation.
Yeah. Yeah.
Okay. It's just temporary.
Exactly.
Okay.
Yeah. Yeah.
Thank you.
Yeah, Manas, please go ahead.
Yeah, so thank you, Professor Anupama, for the talk. I have two questions. The first question being that you showed the supernovae light curves, and I see there is a certain rise, then there is a steady decline. But one of the light curves showing some plateau, and you connected it was the kind of recombination process ongoing, resulting such plateau possibly. So is that this supernova is particularly different from other supernova showing such recombinations, while the others are lacking it?
See, these are the supernovae which have hydrogen-rich material around them, a massive hydrogen envelope. Okay, so these are called as the type 2p supernovae. Okay? So the more amount of hydrogen mass you have in the envelope, you will see the plateau for a longer duration.
I see.
So in the hydrogen-rich supernovae, which have a lower hydrogen envelope, you see a very short plateau duration. So it is primarily connected to the hydrogen mass in the envelope. Does that
Okay, I
answer
see.
your question?
Yeah, I connected it to why it is recombination is lasting for a
Yeah,
longer
yeah.
time, possibly due to the volume of hydrogen you
Exactly,
have
exactly.
in
It's
the system.
based on the amount of hydrogen present in the envelope or the mass of the hydrogen envelope.
My second question is one of your novae. You discussed that the oxygen third forbidden line emission is being detected in the outer part, whereas hydrogen been seen in the very close
Close
to
to
the
the
supernovae somewhere.
yeah.
So I thought, is it we anticipated reverse because of temperature requirement, but in this case you see the difference, and you suggest some stratification of
Yeah,
some of the
yeah. So
hydrogens. So
by inner regions, what I mean is that this particular object had the bipolar cones and the equatorial ring. Okay, the equatorial ring is um, closer to the binary. It's a smaller region, and then you have the bipolar cones, which are more extended. So the density in the equatorial region is higher than in the polar cones. Okay, and probably the speculation is that there's a lot of circumbinary material around novae, which could be from the common envelope, material from the common envelope that could be there. Now, this particular nova went through a phase where it showed a domination of ion lines. okay, which could be coming from the circumbinary material. So it's likely that the equatorial region is dominated by um, the emission features which require high density. Okay, hydrogen would be present everywhere, but it's more dominated in this region.
Okay, thank you, Viresan. You may proceed.
Yes, I do not see any hands raised at the moment, but in case somebody is having, question, want to ask question, please go ahead. Okay, it does seem that there are no more questions. So now I'll hand over to Dr. Manas Saban, and who will move to concluding sessions. Manas, over to you.
Yeah,
Sorry,
thank you, Viresan.
I was about to ask, I couldn't unmute myself.
Please go ahead.
This is Nandita here. Okay, so I actually wanted to know how many, I mean, is it rare to observe the interaction of supernovae with CSM? You showed some example, but not aware whether this is a common phenomenon, or particularly in context of observation from astrosat.
Supernovae with CSM.
Yeah.
Okay, so see, initially it was believed that there are very few supernovae where you have dense CSM which show up. Okay, so these were primarily showing up as very narrow hydrogen features in the spectrum, which lasted for a long time. And it was believed that this was coming from the shock interaction of the nova ejecta with the CSM. But of late, with the detection of supernovae almost immediately, during the shock, after the shock breakout, the presence of CSM in these objects is becoming, I mean, it's no longer such a rare phenomena.
Okay.
They might not necessarily show the narrow features that one sees in some of these systems with dense CSM, but then they do show up either as the flash ionization features. That is, you see for a very brief period, you see very high ionization, narrow features in the spectrum, okay, which is a clear indication of it coming from a very slow moving material, which obviously has got to be a CSM and not the supernova ejector, which travels at very high velocity, right? Or sometimes you don't see such flash ionization because you might not have observed it very early in the immediate shock breakout phase, but you do see signature of a CSM interaction in the luminosity. So when we model the luminosity with these various analytical models, you find that you need an additional source of energy. And that additional source of energy is probably coming from the CSM
Yes.
interaction. So it is becoming more and more evident that you do have CSM signatures. But again, I mean, this is only because there has been this rapid follow up of the objects once it is discovered.
There are several such events
There
in.
are now a lot of core collapse supernovae are showing this signature, particularly the type 2p kinds, where you have the massive hydrogen envelope present. Those are showing up more, probably because there is more material present there or something like that, and those are showing up more. Yeah. Coming to the astrosat thing itself, well, one does expect to see the shock breakout in the X-rays, for instance. UV observations are by far very few for supernovae so far. Probably because you didn't have that sensitivity, and most of the objects are distant. I mean, there are a few which are being studied with the HST, the very early phases again. And this particular supernova we could observe with the astrosat because it was just very nearby. And we were lucky that the astrosat FUV was working and we could get a spectrum of it, and very early on. Okay. Normally, what happens with the FUV is that initially you see it, and then when the ion lines, the Fe2 lines, begin to be seen in the optical, you have the ion line blanketing, Fe blanketing as you call it, right? Because of the optical depth becoming high. So at that time, it suppresses the UV flux. So you can't observe it in the UV during that period with the existing facilities.
Okay. Thank you.
Professor Anupama, this is Mudit here, if I'm allowed to
Yeah.
ask a bit.
Sure.
You ask about the sensitivity of UV, the UV telescope. So what do you think in order to capture the earliest phase of the supernova, let's say for the median redshift? I mean, I don't know whether it's a 0.05 or zero 0.1 or something like that. Would you guess that what should be the suitable aperture of an UV telescope equipped with the medium resolution spectrometer kind of thing?
Okay, I mean, astrosat, we couldn't do much because for various reasons. I mean, astrosat's TO policy was such that, I mean, what you need is a swift kind of response to be able to observe transients. Swift has observed a few supernovae, but it's a small telescope. And mostly the UV emission has been from the core collapse supernovae that it has been observed. HST has observed a few, but again, I think HST is also, you have the scheduling issues and things like that. Okay. So definitely something like a 1 to 2 meter class telescope with the, the rapid scheduling like the Swift will increase the number of supernovae that you can observe in the UV.
Okay.
So I think that is what would be. I'm talking of particularly if you want to get spectra.
Okay, sure.
And not photometry, spectra.
Yes. Okay.
Yeah.
Thank you.
Okay, so yeah. Good afternoon, everyone, and it's my privilege to propose vote of thanks for today's Pyaril Ka Amrut Vyakhyaan. On behalf of Pyaril Ka Amrut Vyakhyaan committee and the entire Pyaril community, I extend our heartfelt gratitude to Professor G.C. Anupama for delivering such an insightful lecture on time domain astronomy. Particularly, you all might have noticed how today's lecture beautifully illustrated how time domain astronomy enables us to explore physics of the most energetic, rapidly evolving phenomenon of the universe, including novae, supernovae, gamma ray burst, gravitational wave, and accretion power transients. Professor Anupama also emphasized the importance of rapid multi-wavelength and multi-messenger follow-up observations. As you might have noticed throughout the talk, various observations through GMRT, AstroSat, and IGT, and Hanley telescope, and other international facilities. She also highlighted the significant role of the 0.7 meter robotic Growth India telescope at the Indian Astronomical Observatory, Hanley, in global transient follow-up observations, demonstrating how coordinated observation efforts are required for advancing our understanding on the dynamic universe, or you can say the restless universe. Professor Anupama, thank you again for your valuable time and for sharing your experience, expertise with us with this exciting field of time domain astronomy. Thank you.
Thank you.
On behalf of Vyakhyaan committee, I'd also like to express my sincere gratitude to Professor Anil Bharadwaj, Director of PRL, Professor Palam Raju, who is now absent today, Dean PRL, for their constant encouragement and guidance and support in ensuring that this series keep going unhindered. Our sincere thanks to all the participants, both those present in this platform as well as joined through YouTube, for your enthusiastic and participation and valuable time. With this, we come to close of today's Amrut Vyakhyaan. Please visit us and our social media platforms for our announcement and next Vyakhyaan. Thank you all. Have a wonderful day. Thank you.
Thank
Thank
you.
you, Professor Anupama.
Thank you.
Thank
Yeah.
you. Thank you, everyone.
Bye.